All right, welcome back, class. As I've told you a couple times now, the next two topics we're going to do are actually two full units. So this week we are going to go through an entire unit. We're not going to be able to hit every outcome in the unit, but we are going to get to ones that are maybe more important to Physics 30 or math coming up or anything like that. All right. So this week you're going to be talking, or I'm going to be talking, you're going to be learning about energy and the conservation of energy. A lot of this is similar to what you have done already in Science 10, so it should be pretty straightforward, I hope, but we'll see how it goes. So first we need to talk about energy. What energy is it is the ability to do work. All right. If energy has the ability to change objects, energy has the ability to change an object's shape, its speed, or its location. All right, if it, again, changes its shape, if it makes it move at all, or if it changes where it is. Energy is also a scalar value, so direction is not going to be important to us. We're only caring about the magnitude, and it's measured in joules. So what is a joule? We can use unit analysis to find that. Back in Science 10, you would have learned a couple formulas. One of them being potential energy is equal to mgh. For that, we have your energy, again, we give joules as its unit. Mass, we measure in kilograms. Acceleration due to gravity is measured in meters per second squared. And the h means height. Height is measured in meters. So when you combine this all together, joules are equal to kilograms times meters squared per second squared. We can also look at the other formula given for kinetic energy. And kinetic energy is equal to 1/2 mv squared. Again, joules is what we measure energy in. So we have joules is equal to our mass is kilograms, right? Because 1/2 doesn't have any units. Velocity is measured in meters per second, and that's all squared. When you distribute in, you have joules are equal to kilograms times meters squared per second squared. There are 5 types of energy that are important to us in Physics 20. The first type of energy that's important to us is potential energy. All right, what potential energy is it is energy that is stored in an object due to its position or state. All right, so it means it has a potential to move. It has a potential to go. The one you may have talked about in grade 10 or in Science 10 would have been gravitational potential energy. So that is when energy stores in an object based on its height above a chosen reference. So for example, if I have a pendulum and the ball is sitting on a pendulum, if this ball swings up and now is sitting over here, it is higher up than it was before. So before, let's say it had a height of 5 centimeters above the ground. That does not mean that its potential energy will be based on that 5 centimeters. Its potential energy is based on its equilibrium point. So that's where it's sitting when it is at rest at its very lowest point. So we actually would consider this to be the 0 centimeters. Meaning if this now is 10 centimeters above the ground, it would actually be 5 centimeters that we would take as our measurement. It's 5 centimeters above that equilibrium line. Alright, so its potential as it gets higher and higher has a greater gravitational potential energy. The formula we use for it is potential energy is equal to mgh. Again, you know this is mass, this is acceleration due to gravity, and this h, it stands for height. But remember, it's the height above the reference position or the equilibrium point. So height above, I'm going to say reference position. It's that height above where it's the lowest point, not the ground in this situation. The next type of potential energy that we have two that we worry about in Physics 20, is one you may not have seen yet. And we call this elastic potential energy. What elastic potential energy is it is the energy that is stored in elastic objects due to it being displaced from equilibrium. So what that means is when I pull an elastic band apart, it wants to go back, right? It wants to get back to that original position. But it's got all that potential energy because when I let it go, it's going to snap back to its equilibrium. That's what Hooke's law is. Hooke is a scientist, and he found out that the restoring force, or the force that wants to get that elastic band back to being in equilibrium, is directly proportional to the displacement of the equilibrium. So what that means graphically, if you have your graph and you have your elastic potential force, or your spring force, your force that wants to get it restored back to normal, and you have your displacement, they are going to be directly proportional. The further you stretch an elastic band, the greater the force wants to get back to its original shape. Alright, so for elastic potential energy, the formula you're going to have is EP is equal to 1/2 kx squared. So EP again is going to be potential energy. What the K stands for is the K is the elastic or spring constant. The word constant in here is maybe a little misleading in that it is not the same for every single situation. Each scenario or each example is going to have a different elastic spring constant. The reason it's constant is because no matter how far you pull that elastic band, it has the same value. Alright, that value doesn't change in that entire situation. And then what the X stands for is the X is equal to displacement. Why it changes to X now instead of D, I'm not sure, but that's what it does. I think a big reason is because, I don't know, and displacement is measured in meters. Alright, so if you're looking at Hooke's law, you know that it's wanting to get back to its equilibrium position. So you're going to know that these force that wants to get it back is equal to the negative spring constant times the displacement. Alright, that is going to have something to do with the slope, which we will get to later in the notes. The next type of energy we're worried about, and again this goes back to grade 10, is kinetic energy. So what kinetic energy is, it's any energy of motion. So if something's moving, if it has any type of speed, it has kinetic energy. And the formula that we use for kinetic energy is energy, or EK, is equal to 1/2 mv squared. So when we put that all together, we get mechanical energy. Mechanical energy is the sum at any instant of the potential and kinetic energies of an object. So mechanical energy is kind of like the net force in a way, but this time we're talking with energy instead of force. It takes both the potential energy and the kinetic energy acting on the object or on the scenario, and it adds them together. So mechanical energy is equal to potential energy plus kinetic energy. Alright, this is not on your formula sheet. What you're going to end up doing a lot of times with this is you'll get your mechanical energy and you're going to plug in your formulas for potential and kinetic energy. So you're going to have it's equal to mgh plus 1/2 mv squared. Again, this is not on your formula sheet, but it is something you're going to need to know and understand. Alright, let's look at a couple of energy examples. Actually, quite a few energy examples. So the first one tells us that we have a 900 kilogram elephant is walking up and down a hill. At its highest point, the hill is 32.5 meters above ground level, with a flat portion located 18 meters above the ground, which is point B. Alright, so the height at point B is equal to 18 meters. And its highest point is going to be at C, and that's going to be 32.5 meters. The other thing we know that the mass of this elephant is equal to 900 kilograms. So our first question wants us to determine the gravitational potential energy relative to the ground if the elephant is at point B and point C. So let's first split this up and look just at point B. At point B, we know our formula for potential energy is potential energy is equal to mgh. So our mass of the elephant doesn't change. It's always 900 kilograms times our acceleration due to gravity, 9.81 meters per second squared, times our height. But since we're at point B, we're going to use our height at point B. So our height at point B is 18.0 meters. When you plug that all into your calculator, you're going to get an answer of 158,922 joules. Taking into account significant digits and scientific notation, your potential energy at point B is going to be 1.59 times 10 to the 5 joules. Alright, I'm going to leave point C for you to do. The only difference with point C is, again, your mass stays the same, your acceleration due to gravity is going to be the same, but your height, instead of being 18 meters above, you're now going to be 32.5 meters above. So that's for you to find out. The next part of this question wants us to determine the height of the elephant if he has 5.34 times 10 to the 4 joules of gravitational potential energy. So what we're given in this question, again, we know the mass, we know the acceleration due to gravity, and now we have the potential energy. So using our formula, potential energy is equal to mgh. We want to rearrange and solve for h. So to do that, we are going to divide both sides by mass times gravity, and our formula is going to be h is equal to potential energy over mass times the acceleration due to gravity. That is equal to 5.34 times 10 to the 4 joules, as given in the question, divided by the mass of the elephant, 900 kilograms, times the acceleration due to gravity, 9.81 meters per second squared.